Hi everyone, this is Yukai coming to you from the West Coast. I'm very sorry to miss the first day of class. Definitely would have liked to meet you guys, but I've got 2 meetings this week on the West Coast, one in San Diego yesterday and one in Seattle on Friday, and I just didn't want to make 2 trips to the West Coast in a week. That's a lot of flying, that's a lot of carbon. Plus, what is going to happen on the first day of class is typically not super important, especially since I was not planning on covering any technical content. I was going to go over the syllabus, which is now posted on the course website. You guys can all go take a look. Let me know you guys have questions. And I was going to go over this deck of slides, which is also available on the course website. A lot of things available on the course website. You guys should get used to checking it. But I was going to go over this deck of slides that basically covers the course content, gives you an overview of what's to come. This is not super important in the sense that none of the technical developments that we are going to see will rely on you knowing this content, will build upon this content. This content is really just sort of the context maybe for the subsequent technical developments. And so since it's not super imperative, this course content, I'm just going to wrap it up in a YouTube video, put it up, and so you guys can watch at your leisure. I'll recommend you watch this before class next Monday. Folks, here we meet our first mathematical optimization problem. This is what traditionally people will call a nonlinear programming problem with inequality constraints. The notation here is actually fairly self-explanatory. You minimize this cost function or objective function subject to these constraints. But I'm going to unpack this a little bit. One, to pin down some terminology, and two, to point out several conventions that are at play here, that are in use here. So what is the English version of this optimization problem, if you will? Well, you take this vector. This is a vector of n variables. Let's call them your decision or your optimization variables. You are going to try to find, quote unquote, good values for these variables that, one, satisfy the constraints, meaning that if you evaluate these constraint functions, fi, at your chosen variable value x, you will find that all these fi's are less than their corresponding bi's, their corresponding right-hand sides. Second, among all these settings of x that satisfies these constraints, you want to find the one that leads to the smallest value of f sub 0 of x. F sub 0 here again is the cost of the objective function. Some terminology. So any x that satisfies all of the constraints, we call them feasible. These constraint functions, we've sort of written them with a non-zero right-hand side, right? You're looking at the constraints fi of x less than or equal to bi. But usually what we do is we sort of absorb the right-hand side, we absorb the bi into the definition of the constraint function, right? You could equivalently write these constraints as fi of x minus bi is less than or equal to 0. And this is usually what is done. So the right-hand side, these bi's are usually just set to 0. Finally, we are writing this optimization problem as minimize. Now, this is just convention. It's convention to think about problems as minimization problems. You could, of course, think about problems as maximization problems. In fact, there are whole fields, especially economics, that do think of problems that do go with the convention that optimization is typically stated as maximization. And this is, there's nothing really deep about here. It's mostly because in econ, they always talk about utility maximization. And so it's just very natural to maximize utility functions. For this optimization problem, there are 2 solution concepts, I would say. The first is the min, and the second is the argument. Okay. So the min, this you could think about the solution concept is a scalar. Okay. It's telling you it's asking what is the smallest possible value of f0 of x, where x is constrained to satisfy the constraints. Okay. So again, the min is a scalar. Okay. The argument, on the other hand, is a vector. The argument is the value of the optimization variables. This is this vector x1 through xn, is the setting of this optimization variable. It's the value of these optimization variables that achieves the min. So f0 of the argument will give you the min. Okay, these are the 2 solution concepts. a lot of instances of this generic optimization problem that we've seen. I've listed some of the applications here. Not all of them have to do with statistics, but quite a few of them are statistical. In particular, all the ones under data fitting, right? These are inherently statistical. Portfolio optimization, which is a subproblem, is a problem that arises in mathematical finance. This is also has a statistical element to it. We will spend a considerable amount of the class going over applications. This is the part of class that follows duality and before we get to algorithms. And here you really see the flexibility and the generality of this optimization technology. So there are many problems that you can write in the form of an optimization problem. Now, unfortunately, it is generally very difficult to solve optimization problems. So being simply able to write a problem in the form of an optimization problem, simply able to formulate a problem as an optimization problem, this is oftentimes not helpful because you still have to solve the optimization problem. It can be quite hard. In fact, a general optimization problem is, you can show that this is NP-hard for those of you who are familiar with computational complexity theory. Fortunately, there are some exceptions to the rule. There are certain classes of problems, certain classes of optimization problems that we know can be solved very efficiently, in the sense that there are efficient algorithms. There may even be efficient implementations of these algorithms. So these algorithms are not sort of purely theoretical. The two special cases that we'll talk about in a little bit in this lecture are least squares problems, which are, I would say, a special case of quadratic optimization problems, and linear programming problems or linear optimization problems. Both of these fall under the umbrella of convex optimization problems. Now, convex optimization problems, they're in some sense they're a special case. They are not, it's actually false that you can solve all convex optimization problems efficiently. Convexity turns out to not be enough, as much as, whatever the folklore out there is saying. There are convex optimization problems that are NP-hard. However, for convex optimization problems that emit certain computation oracles, so for example, a computation oracle would be like the ability to compute the gradient of an objective function. So assuming that you can compute the gradient of the objective function efficiently, or assuming you can check whether a point is feasible or not, and if it's infeasible, the oracle will provide you with a separation oracle. When you have convex optimization problems that come with these oracles, then they become efficiently solvable. And so convex optimization just turns out to be this problem class that has been extensively studied, and it turns out that a lot of them emit efficient solutions. Okay, so one of the problem classes I mentioned earlier is least squares. I said that this is a special case of quadratic optimization, and hopefully you guys have seen problems like this before. If you guys ever took a class on linear models or on regression, then basically, if you think about it, that whole class is about taking your data analysis problem and boiling it down to solving one of these least squares problems. And so you can do a lot with just least squares. This problem class has an analytical solution, right? You can write down in closed form what the argmin is. And not only that, there are a lot of efficient and reliant algorithms and implementation of these algorithms that would solve these problems for you. The computation time for solving this type of a problem is roughly n squared k. So here n is the dimension of the optimization problem, the size of the optimization problem. It's the dimension of this vector x. And k here is going to be the number of rows of A. Okay? So the notation is slightly different from traditional statistics notation. So k will be the sample size, and n here is the problem dimension. The computation time again here is n squared k. Okay, and so this is, in some sense, you could think about it as quadratic you could think about it as cubic in total, right? There's three factors of problem dimension, some version of some measure of problem size sort of multiplied together. What is very interesting is that despite the fact that you hear a lot about least squares, there are other optimization problems that have very similar computation times, but you don't hear about them as much. We'll talk about that on the next slide. But the point is, this is a very mature technology, and so you can essentially solve least squares problems these days without knowing how the least squares problems are solved. Like you can reliably just call a package to solve this problem. You don't really need to know how it's solved because these packages that you're going to call, they essentially never break. So you don't need to know what goes on inside because there's never ever going to be a need for you to go in and fix when something goes wrong. Now, you can actually probably teach an optimization class on just using least squares. I mean, in some sense, your linear models class, your regression analysis class is essentially just saying, what is the set of data analysis problems that least squares can solve? And it turns out to be a fairly large set of data analysis problems. So now let's move on to this other problem category that I mentioned, linear programming. Note the word programming really just means optimization. I guess I haven't said it thus far yet, but programming just means optimization. And in fact, there is a group of people who are trying to do away with this terminology of programming. It's there for historical reasons. And so any time you hear the word programming, you're going to hear a lot linear programming, quadratic programming, cone programming, semi-definite programming. You can just replace the word programming with optimization, and that's basically what it means. So what is linear programming? Linear programming is just optimization, one of these generic optimization problems where the cost function, the objective function, and the constraint functions are all linear. Okay, so I've written in linear function here just means that this function is just taking an inner product with a fixed vector of coefficients. So here, C is the vector of coefficients that encodes the cost function, and A sub I is the vector of coefficients that's going to encode the ith constraint function. Now, what is distinctly different between linear programming and least squares is that there's no closed form solution for linear programming. You cannot write down what x star is. You cannot write down what the argument is in like a nice simple formula in terms of the AIs and the Cs. Okay, so this makes it very different from least squares. However, everything else is the same. There are very reliable, very mature algorithms and implementations of them to solve linear programming problems. Furthermore, the time complexity of solving linear programming problems is actually very, very similar to the time complexity of solving least squares. Okay, it's again quadratic in the problem dimension or quadratic in the number of decision variables, and it's linear in this case the number of linear constraints. Okay, so it's still overall a cubic computational cost, and it is quadratic in the problem dimension in n. Oh, I should say, these computation times that I'm reporting are essentially counting the number of floating point operations, so add, subtract, multiply, divide operations that you need to do in order to solve one of these problems. So the thing to note here is that in some sense, for all practical purposes, linear programming problems and least squares problems are about the same difficulty because they take roughly the same amount of computational expense to solve. Okay, they're both cubic in the problem input sizes. And furthermore, they're both very mature technology in the sense that you can find a lot of algorithms and even a lot of implementation of these algorithms to sort of solve them for you. Right? To you as the end user, there's very little difference between the two because all you're going to do is going to take a software package and solve these problems. The software packages are very reliable. They seldom break, so you don't really need to know what goes on inside the software packages. We're actually not going to talk so much about what goes on inside linear programming solvers. It's actually a very fascinating subject, but it's a little niche these days. And because the technology is so mature, you're never going to have to open up the solver. There's no real point in me sort of telling you what goes on inside. What I think is very interesting is that you hear so much about least squares, and there's so much, people have tried so hard to use least squares to solve their problems. And this is what you see in your linear models and your regression classes, right? People have taken this least squares problems and really used it to solve all kinds of data analysis problems. But you hear so much less about linear programming. And it may be because that you don't have a analytic solution for the argument in a linear programming problem, but I would be somewhat skeptical of that explanation because, again, solving linear programming problems and solving least squares problems from a computational perspective, they are about equally as hard. What I suspect is really the reason behind it is that linear programming problems are, in some sense, a little harder to recognize than least squares problems. Least squares problem essentially is some type of data fitting problem, right? You try to minimize the discrepancy between your predictions and your what the predictions is supposed to be and your target values, and this gives rise to a least squares problem. Linear programming problem, much more general, much harder to recognize. I'll mention that there are very prominent instances of data fitting problems that are linear programming problems. So, for example, in your let's say your regression problem, if you replace the quadratic loss, the square loss, with a L1 or an L infinity loss, then you automatically very easily get a linear programming problem. But linear programming problems linear programming as a technology is so much more applicable than least squares that it just becomes harder to recognize when you have a linear programming problem. We'll see lots of examples later on. And so that might be the reason why linear programming is not as widely used as least squares. Brings us to the subject of, at the very least, the first part of this class, convex optimization. Convex optimization is simply an optimization problem in which the cost functions and the constraint functions are convex. We'll learn what this is and the implications of that in the rest of this class. But at this point, all we need to know is that least squares problems and linear programs that we just saw, they are special cases of convex optimization problems. The story of convex optimization is a little more nuanced. Generally, you can solve convex optimization problems. However, it is not a guarantee. Generally, there are no analytical solutions. However, there has been a lot of algorithm development in this area, to such an extent that today you can probably solve any moderate-sized convex optimization problem pretty reliably. It's almost a technology in that sense. The cost here, if you notice, is also quadratic in the problem size, the input sizes. But there's this factor f, which is the cost of evaluating the functions and their usually first and sometimes second derivatives. Now, this f can be quite large, and this f is sometimes the limiting factor whether you can solve a convex optimization problem. This goes back to the comment I made earlier about oracles. So you can think about f as the cost of evaluating such an oracle. This oracle could be a gradient oracle, so computing the gradient of the cost function or computing the gradient of the constraint function. It can be a feasibility oracle. So this is a subroutine that would, given a query point x, would tell you whether this point is in the feasible set or not. Does it satisfy all the constraints or not? And if it doesn't satisfy the constraints, it will provide you with a separating hyperplane, so a plane that separates the feasible set from this point, from this query point. This type of oracles are very important in the development what are called cutting plane algorithms that we'll see later in the class. So if the cost of evaluating one of these oracles is astronomical, then there's no practical way to solve this convex optimization problem. So convex optimization problems, solvable, but relying on the ability to evaluate one of these oracles. They are more difficult to recognize than even linear programs. As you can see, there'll be a whole part of class where essentially it's almost just tricks about how you sort of make problems convex. And so they can be sort of quite well hidden. And so using them becomes, more of an art, and it takes a lot more training to be able to properly use convex optimization. However, people have found a lot of ways over the years to formulate problems as convex, and this is what the modeling part of the class is about, is to how you model, how you take problems, formulate them to be convex. That was about the modeling part of the class. The other two parts of class, modeling will take up, I would say, maybe close to half the class, so it's a pretty big aspect. And the reason why modeling is such a big aspect of the class is really for a lot of the problems that you guys will encounter, it is safe to treat convex optimization as a technology. So you don't really need to know what goes on once you formulated the problem as convex. You don't really need to know how to solve it, because there will be some off-the-shelf solver that would do it for you fairly reliably. However, for the few cases where you do actually need to get your hands dirty and try to solve the problem yourself, we're going to talk about some algorithms. Note, this is not an exhaustive list of algorithms. This is actually a very partial list of algorithms. These algorithms on this list were chosen because they are likely the algorithms that you are going to have to implement. They're not the workhorse algorithms of convex optimization. In fact, usually if you have to resort to implementing one of these algorithms, you are already sort of, facing one of the harder problems, these are one of the problems that the off-the-shelf algorithms does not solve for you. Incidentally, the off-the-shelf algorithms that I keep talking about are what's called interior point methods. There's a lot of literature on them. You can go read up on them. There's a beautiful theory behind it. But we will not talk about these algorithms at all. Instead, the algorithms that we're talking about are roughly first-order algorithms. So you hear a lot about these algorithms in training deep neural nets. Stochastic gradient descent is an instance of is a stochastic version of one of these algorithms. But we'll see, the rest of the family. There are also what I would call meta algorithms, which are these decomposition and splitting methods. And so they essentially are ways you can take a convex optimization problem and boil them down into simpler convex optimization problems. You still have to apply some solver to solve these simple optimization problems, but you can, through this intelligent use of these solvers, solve this more complicated optimization problem. So this is decomposition and splitting algorithms. And that's going to wrap up the algorithm section. At the very end, we'll have a little bit, a small part on theory. So here the focus is really going to be on how you characterize the optimal value, how you characterize the optimal solutions. And since we're looking at applications in statistics, we're also very interested in how sensitive they are when you change the problem parameters. Because as we'll see, when you have these optimization problems arise in statistics, the problem parameters, so the specifications of these cost functions and the specification of these constraint functions, they're oftentimes data dependent. And so since they're data dependent, therefore they're random. And so you are interested in making the solution of this optimization problem somewhat robust to the randomness inside these constraints or inside the cost function. And so we're going to spend a little bit of time looking at perturbation of optimization problems.